Okay, well, welcome back from your spring break. Now we're going to push to the end, right?
Yeah.
This is the time when you get really strong and push hard, finish strong, right? But, you know, summer is coming. I know you got spring fever maybe starting, but don't give in to it. Now's the time to work hard and buckle down and finish off with the finals and stuff. So this is the run to the end here. So back to chapter 5 and physics for realists, E&M. And so to remind you where we are here, we're going through these chapters 2 through 5 are different approximations that we deal with in order to build up to the full Maxwell's equations. And remember, the idea of these behind this textbook is to consider certain things, freeze out other stuff, don't consider other things, focus on one particular thing at a time, then go back, and now let's put something else back in and see how and understand that in isolation, but then go back and consider them together, and so forth. So this is the strategy that whereby we figure out things, so we've been doing that here. The why is that gone? That's not showing up. Why is that not showing up? The screen is not on. Huh. Was it on at all? I didn't actually look.
I never saw it.
And that one's not working. Does that work sometimes? I don't pay any attention to that. That's never been. Wow. Hello. Why is that? Excuse me just a second. We have a technical issue here. Why is that not working? That's kind of makes it. Everybody turn around and look at the screen back there, I guess. That's just ridiculous. Huh. Wow. I haven't had that happen before. I really, that's a new one on me. If I switch over to the lectern computer, it still doesn't work, does it?
Does the projector need to be turned on?
We could hit the power button with the projector.
Yeah. Oh, yeah, that's okay. Yeah, we need a ruler or something. Anybody? I don't want you to stand on one of these.
I feel confident.
You're pretty tall. Can you reach? Hey, okay.
Easy.
All right, good for you. Good job. Did you feel any insecure or kind of?
I felt like a moment of worry that I want to be able to make it.
Yeah. That normally. Okay, there it is. It's coming on. Thank you, Mr. McKee. Oh, that's right. I'm going to save the day. So, what's that?
Ben was the brains behind that.
Oh, that's right. Yeah. There's the thinker and then there's the doer. You gotta have both though, right? The thinker's going to starve because he doesn't know, but the doer's just going to wander around doing crazy things. So you gotta have both. Okay, so we're doing these chapters 2 through 5, and we're building up this successive level of approximations here, or successive abstractions. First one was electrostatics, where the charges stay put. Then we consider stationary current loops. So the loops don't move, the current in the loop stays fixed, and the current has to flow. There's no charge building up anywhere. So that's magnetostatics. Then we considered magnetic induction, where we allowed the loops to move, or for the current to change in the loops. And then we saw there's a lot of stuff that goes on, a lot of interesting in magnetic induction. And now we're getting to the last quasi-static effect, which is not a very descriptive title. It's the last thing we're considering, but that doesn't really tell you very much. So specifically what we're doing here is now we're allowing charge to build up, so that we're cutting off the end of the wire so the current can flow into the end of the wire and build a current, or in other words, capacitors. We briefly considered capacitors in chapter 2, but we really didn't consider it. Really, it wasn't the proper time to consider it, because in electrostatics, you shouldn't have even current flowing, right? But we considered capacitors briefly in chapter 2. But now we're going to do a good job with capacitors. We're going to study the electric and magnetic fields around capacitors as they charge up. And we'll find then, and in all these cases, all 4 of these chapters, we considered instantaneous propagation. That is, we neglected how long it takes for the change in the source to end up altering the field at some distance from the source. So the fields are present in the plana, and we change the source in some way. It takes time for that news to reach the location out here. We're neglecting that time. It's just instantaneous, okay? So that hints then that chapter 6 will be to put in the propagation. And that's really the interesting thing about chapter 6. One of the interesting things that we'll cover in chapter 6 is radiation. We'll move the source, and then we'll watch the fields propagate, the changes in the fields propagating outward. Okay, so here we are in chapter 5 then, and we're going to learn more about how current is a causal agent. And of course, what we mean by current, that's shorthand for a massive substance with charge and impetus, or a massive substance with parts virtually present that have charge and impetus virtually in them. Okay, so it's shorthand for impetus activated charge. Okay, before we had the case that J had to be circulating. In other words, the divergence of J was 0 before. And now we're going to relax that condition. We're going to allow J not to be circulating. Okay, and that brings in the Helmholtz decomposition. And this is a very nice way of helping us to figure out what's going on, is to break up these things formally, not physically. It's just mathematical decomposition. And as I pointed out before, this is not ordinarily done at this level of freshman physics. Usually you don't get to this until the junior year. But I think there's a lot of physical insight to be gained by this, and so I really like that this is done, in addition to using the scalar and vector potentials a lot in this book. Those two things really, I think, really help to add depth of insight. And so we're going to, by use of the Helmholtz decomposition, then we can justify that vector fields can be separated into two parts, which we call in the book curling and diverging, which is not quite right. The curling part is not diverging, and the diverging part is not curling. So this really should be called U not diverging and U not curling, would be the more precise thing. But shorthand is going to be curling and diverging parts. So any vector field can be decomposed this way. There are some restrictions on this, and so what we'll say is for the consideration of the things that we're talking about, we can do this, so that these fields are, for example, currents or electric fields and magnetic fields produced by sources, and there are some restrictions on this, but those restrictions apply in this case. So there's some caveats here that I'm not talking about, but they're really not restrictions for us. Okay, so you can resolve any vector field into a part that has no diverging part and a part that has no curling part. So let's do that, for example, to the electric field. And we found before that for the electrostatics that the electric field had only a diverging part. And then when we added in the magnetic induction, we found a curling part to the electric field. We also found before that in all cases, everything we've considered up to this point, the magnetic field does not diverge anywhere. And that's because there's no magnetic monopole. And so there is no diverging part of the magnetic field. The magnetic field always is this part that is not diverging, the B sub C. Whereas the electric field has both pieces, and the diverging part is generated by just charge, bare charge sitting there, causes this hedgehog electric field diverging from it or pointing inward to it. And the curling part, remember, we found in magnetic induction. There was a piece from the A dot effect. Okay, so we can also decompose the current density. And previously we considered only J sub C. Remember we said the divergence of J was 0 before. And if you remember, the divergence of J is negative rho dot. If the current is diverging, then charge is building up somewhere. So we considered that divergence of J was 0, so there was no charge building up anywhere. And if somebody reminds me, I'll email you these slides. If you remind me to do that, I'll send these. In fact, I should have done it before the lecture so you could write on it instead of just taking notes. So but if you'll remind me, I'll do that. As well as I have similar view graphs for chapter 4 that I'll send out. Okay, so previously we considered that JD was 0. So in effect, what we're going to do is to put that back in. And so when we were doing magnetic induction, where the divergence of J was 0, we had that a magnetic field was generated by a current, but specifically we had JD was 0, so we should have on the right-hand side of this, we should have put a subscript, J sub C. Remember Maxwell's equation, second equation, was that the curl of B was 4 pi over C J. We should have put a J sub C there because we had the condition that JD was 0. So it shouldn't have been J. It should have been just J sub C. And the thing that we're going to find out here is that a diverging J doesn't cause a curling magnetic field. Okay, so previously we considered that JD was 0. And remember, we have this condition here. This is called the continuity equation or the conservation equation, and expresses conservation of charge. The divergence of the current is negative rho dot. And that means at any place where the current is diverging or converging, you'll have charge building up. If the current is diverging outward, then you're losing charge. It's becoming more negative at the origin. Or if the current is converging, then it becomes more positive. You get positive charge building up. I still don't see the camera. There's supposed to be a camera, and so I'm worried now. I'm sitting here making these gestures, and I'm not sure that the camera's picking it up. In fact, I'm pretty sure it's not. So, okay, so I'm going to have to try to be sure to describe these things verbally better. Okay, so just as charge creates a diverging E, diverging J also creates a changing E field. Right? And that's because of a diverging J, causes a charge buildup, and charge generates an electric field. And the diverging J means that charge is building up, so that means that the electric field is going to be changing in time. So a diverging J is going to be related to a time-changing electric field. Okay? And so, remember we have the continuity equation there. And if we have this relationship here, we have the divergence of J is negative the time derivative of rho, then we can actually back out the relationship between the diverging piece of the current and the time derivative of the electric field. So the way to do that, let's see, I'm going to try to do this here. Back over here to this. Okay, so recall that we have that the divergence of the electric field is 4 pi rho. That was Maxwell's first equation. Okay, now let's take the time derivative of this. So I guess first we should take the time derivative of both sides. So we have the time derivative here. And rho dot, by the continuity equation, is related to the divergence of J. Okay, and the other manipulation here is to notice that the time derivative and the spatial derivative commute. The order of second derivatives doesn't matter. We found this when we take second derivatives. We have multiple functions of multiple variables. The order of the second derivative doesn't matter. So we can rewrite this as the divergence of the time dependence of E like this. Okay, so that hints at a relationship between the time dependence of E and the diverging part of J here, the diverging part of E and the diverging part of J. Okay. because we have the divergence there, we're filtering out the part that might be curling. Okay, so that hints at this relationship between the diverging part of the current. It creates a time-dependent electric field. And I'll show you how this works. Okay, so remember we said that the curling part of J causes a curling A and a curling B. And so now we're trying to figure out what does the diverging part of J create. It doesn't create a magnetic field. It doesn't create an A field. It doesn't create a magnetic field. Let me give you a specific instance. Suppose we had a charged sphere that is a sphere with charge placed on it, and we blow it up. We put an explosive inside, and we explode the thing. Now we have the current coming straight out. So there's no curling. The electric field doesn't curl. J does not curl. It diverges. That's a really simple way to create a diverging J. That would not create a magnetic field or an A field. There'd be no A field and no B field from this. So Mr. Bacot asked me the question, just as we considered this last time. We had a current-carrying wire. We had current in it. And let's suppose that the current is distributed uniformly through the cross-section of the wire. Let's just suppose that. Here's J here. So J is flowing through the wire like that. And the total of this is I, is what we call I. We integrate J over the surface area here, and we call this I. So the total of all of that would be I. Why does how does that curl? That doesn't look like it curls at all, right? We said it curls because it flows around in a loop, but it also does curl. If you look at it right at the surface here, if we put a flow meter, a curl meter right here at the surface, there's no current outside the wire, there's current inside the wire, so this thing would spin this way. So there's curl. J curls, there's a curling part of J right on the surface of the wire if the current is distributed the way I said here, the current density is distributed this way. So there's a curling part of J all around the surface of the wire here, and that's what generates the magnetic field and the A field from this. Okay. All right, so that's so in this case, we don't have a curling J. J purely diverges, but you can see why the electric field would be changing because you're moving the charge around. And the charge distribution is what generates the electric field. So the electric field is going to be changing in time. Okay. So now let's go back then to Maxwell's equation, where we have the curl of B is related. Now we recognize that this is just the curling part of J. It's not the full part of J there, because if we put the full part of J there, we would get something else. We wouldn't get the correct thing. It's only the curling part of J that should be in here. But it's difficult to work with a piece of J like that. So Maxwell wanted to try to simplify this because it was difficult to extract, to write some way of extracting out from the total current density, how do you pull out the part that's curling? So there's a way to do it, but he argued for a simpler procedure. He wanted to put the total current density into the equations. But in order to do that, he has to subtract off this current density. In other words, this piece, can you see that? No, you can't see that either. Okay. Hang on, I can change this around so I can use the pointer here. No, it doesn't show. Okay, so but you see that the total J is a superposition. It's a sum of JC and JD. So I can replace the JC on the right by subtracting off JD. That's the trick here. And it's an interesting trick to do that. It's an interesting idea. So let's go back over that again just so you can see exactly what's going on. We should have properly on the right-hand side of this equation JC only. But he wants to write this in terms of a total J. So if we do that, then we have to subtract off the diverging part of J. Well, that doesn't seem like you've gained anything, except that we just determined that the diverging part of J is related to the time derivative of the electric field. So I can rewrite this in terms of the electric field. And you're almost there. Yeah. So the purpose of this term is to cancel the JD. Inside the J, to eliminate the JD that's inside the total J there. It's a funny thing to do. It's not a physical argument. It's a purely mathematical argument, that we're doing this in order that we can write the system of equations more simply. And that is Maxwell's goal, is to find a unified set of equations that governs electricity and magnetism altogether. And that's his goal. But at the cost of this unification is he's losing some of the physical insight. Okay, so he's introduced a term here which becomes very famous. This is called the displacement current. Okay, and we'll talk about that here presently, this displacement current. So he's introduced this term. Okay. But this starts to obscure things. That E dot term, the purpose of that is to cancel out part of the J. And that's what it's supposed to be for. And it makes it a little confusing because you're canceling out something, putting something in, having to cancel something out by putting it in. Okay. Now, he also demonstrates that you can drop the D on the E sub D. That you can drop the diverging part of the electric field there. So the complete discussion of that is in the text. Why can we drop the ED there on there? But Maxwell demonstrates that you can drop that part, and you end up with this equation. This is then I always forget. This must be the fourth equation. Maxwell's fourth equation. And remember, the purpose of that last term on the right-hand side was to cancel out part of the J. Kind of odd, right? Now you can forget about why we got there. And in fact, that's what happens. We tend to forget about how we got to the formalism, and we just work with the formalism. Okay, but so that last term is the displacement current, because it looks like a current. Well, it is kind of a term like a current because it's related to JD, right? It is kind of like a current, and it does cancel out part of the current. So it looks like a current, and he keeps it on the right-hand side because he wants to say that the currents on the right-hand side are what generate the magnetic field. But you see what you've done there is introduced a term as a mathematical convenience that's now acting as a source. Looks like a source for the magnetic field. This equation looks like J, total J, and the time derivative of E cause a curling B. That's what that looks like. And in fact, that's what I was told when I was a junior, when I was learning this stuff. That last term actually causes a curling magnetic field. But that's not correct. It doesn't cause a curling magnetic field. Its sole purpose is to cancel out the part of J that also doesn't cause a curling magnetic field. Remember, JD doesn't cause a curling magnetic field either. And so its sole purpose is to cancel out part of. So he seems to have been thrown by this because the elegance of the equation that he has there suggests to him, in fact, to look for a physical source, a physical cause of this so-called displacement current, this derivative of E with respect to T. And this is another aspect of his mechanical ether. Maxwell wanted there to be a physical source for this. After he introduces a term for purely mathematical reasons, he's now looking for a physical cause for it. So this dE dt now, he's looking for a current. And so it's called the displacement current. So let's go back over here. So this displacement current here, he postulates that is actually the physical cause for this displacement current is something going on in the mechanical ether. that there's actually parts of the ether that are moving around in such a way as to generate a current that he calls a displacement current in order to try to give a physical reason for this device, which is purely mathematical in origin. It's not a crazy thing to do, but it didn't work. You know, and so this is further evidence for him that there is this mechanical ether. So the idea of this mechanical ether is that there's something, a medium like air or fluid or something that we're moving through, but it's somehow easy enough for us to move through it that we can never feel it and that we don't see its effects on motion of things, objects. And but it participates, it acts in the presence of these currents and charges and stuff, and so you get these displacement currents that are actually due to parts flowing in the ether. Okay. So that turns out to be a red herring. He's thrown off the course in a sense. He comes up with what he was looking for was a compact system of equations, which he got to describe electromagnetism. But the problem is that he's lost the physical relations of cause and effect, and it happened in those two steps. Remember, the first step was where he put a dot in with the E field. That was we considered an induction. That's properly a magnetic effect, but he stuck it into something that's called electric. And then the second thing is to now cancel off part of J by introducing this E dot term here. Okay. So how do we get out of this? How do we restore a physical causality, a real sense of physical causality? And that's really quite simple. E and B are now confused enough that that's going to cause a problem. And in fact, maybe the best way is for me, let's go back and let's see where we are now with regards to the curling equations. Remember, we had the diverging equations. Divergence of E was 4 pi rho, and the divergence of B is 0. Those are still in that form. But we have the two curling equations, the curl of E and the curl of B. Okay, so this is where we are with Maxwell's equations, and now we have no restrictions on J. Remember, previously we had the divergence of J was 0. Now J, the only restriction is that J and rho have to be related to each other. So the continuity equation still holds. That is a negative sign there that I'm trying to draw. Okay. Okay, so let's study this. Here is the piece where the charge generates the electric field, so that's a connection between the electric field, the diverging part of the electric field is related to rho. And down here is J that causes a curling magnetic field. So rho enters into the divergence equation for E, but J enters into the curl equation for B. But now we have this thing which, in one hand, was introduced for mathematical simplicity, but there's a certain symmetry to it because there's a similar term for the curling equation for E, the time derivative of B. But remember where that came from. Remember that came because that was not a causal equation. Remember that came because he put the A dot into the E field, and that's exactly where this comes from. So this has actually no physical content in it. It just looks like there's some physical content. And this one, the physical content is obscured because it looks like this time derivative here is going to be generating a curling magnetic field. Okay, so here's where the problem really shows up. Let's suppose we have some bodies over here, and we have rho and J. So charged bodies are moving around inside this volume, and but the volume is contained. So we don't let sources go off to infinity. We have some region where the sources exist, and we want to look over here at E and B, over in this location over here. How do the electric and magnetic fields look way over here? And this you could imagine, for example, an antenna. Let's have an antenna. We got charges moving around on the antenna, and that's generating electric and magnetic fields. So it's radiation. And we'll study that in the next chapter, exactly how that works. But just in general, we have this problem where we have some charges moving around. We want to know what the electric and magnetic fields are doing over here. Okay. Now, if we go back and look at these equations, rho and j are 0 where we're looking. So over here, rho and j are both 0 because we're away from the source. So we're in the source-free region. The source is over here, and we're outside of the source, and we're looking at the E and B field. Now let's go look at those equations. Over here, now I'm going to say that these hold only over in this region. The divergence of E is 0, the divergence of B is 0. The curl of E is minus 1 over c dB dt, and the curl of B is 1 over c dE dt. Okay, now we've been led into this by these tricks for making the math simpler, but the temptation is going to be to read in some physical content into these things at this point. And specifically what I was told when I was a junior was that these two last equations are to be read. Changing B causes curling E. Causes curling E. This is this is the narrative, which is wrong. Incorrect narrative. Changing B causes curling E. That's what I was told was that the meaning of that equation, that third equation. And the last equation here, curl of B, was changing E. Oops, changing E causes curling B. And in fact, you get into an argument here. If I take the curl of one of these two equations and on the second time derivative, you get into a kind of circular argument. B causes itself, right? Because if changing B causes curling E, but if changing E causes curling B, then if somehow B could cause itself, and E can cause itself. Okay, do you see what's wrong? What's happened here? What's wrong?
We lose the causes.
Yeah, the causality is completely messed up. What principle does this violate?
Principle of causality.
The principle of causality. Something cannot change itself, right? But here we have the E is changing itself and B is changing itself. In other words, we have this thing, E and B are somehow generating themselves. Well, where did the E and the B come from? Let's see. Here we go. Okay, I got that out of order somehow. Where did the E and the B come from? It came from the source over here. That's what generates the E and the B. So these equations here, hang on here. Yeah, okay. These equations here, these two equations do not have causal connection. B dot does not cause, changing B does not cause curling E. Changing E does not cause curling B, right? What causes a curling B? A J. And what causes a curling E? Well, it was, we stuck in the A dot into the E, and that's what caused it. It was a mathematical trick. So there's not really any causal connection. What is contained in these equations is a correlation. E and B are created by the same source. And so there's a connection between them. They behave in a way that's related to each other because they have a common cause. Okay, so this E and B have a common cause. The same cause, a common cause, in the sense that J and rho are related to each other. They are both generated by the source. And the source is described by rho and J, right? Current, and then it's moving. So rho and J describes the source. E and B have a common cause. And so these equations, the curl of E and the curl of B, in the source-free region, these simply express the correlation. So this is a correlation between things, between effects, generated by the same cause. this is the correct understanding. Not what I was taught, and not what is still in a lot of the textbooks. This hasn't filtered out everywhere yet. You'll still find textbooks that have the wrong causal connections. And so the problem is then that you end up with a confusion about what's causing what, and it gets really, you end up with situations like, for example, we had in magnetic induction where we had Faraday's law, for example, which is an easy thing to calculate, but it could lead to confusing results. If you didn't know the underlying physics, you could be misled by Faraday's law. And so that's an example here. You can be misled by what's going on. Okay, so here's what to do about it. To go back to phi and A. Phi and A retain the connections that we want and are not confused. And so the mathematics still respects the causality for phi and A. And so I'm going to show you that here. So the basic principles to go by, what I want you to remember here, and if you remember this, E and M will not be confusing to you. Right? You'll be spared a lot of confusion. So remember that charge conditions the planet to have an electric field which is further specified by the phi field. So the electric field and the phi field are related. Impedance activated charge conditions the planet around it, the parts of the planet, to have a magnetic field which is further specified by A. But remember, only the curling J creates a B field, and only diverging J creates and diverging J creates a changing E. And then this conditioning gets passed along. But the thing to remember here is that then at the end you have phi and A, and if you have phi and A, you can calculate the forces on particles, which is what you often are wanting to know, is how this field generated by the source, what effect does it have over here on these things? So now that you have the cause straightened out, you have phi and A. Okay, so let's go back here to phi and A. Where are we left with phi and A? Okay, so phi and A, how do we find them? They're generated by charge. And current density. And this is still true here, as long as we're neglecting the propagation time, so this is still instantaneous propagation. So if you have rho and J, you calculate from that. You can determine phi and A. And then you can, if I have a test charge in the presence of a phi and A, then there will be a force present on it, V over C cross curl of A. This is the Lorentz force. And so I can still get what I wanted to get, which is what happens to charges that are present in far away from the source, or some distance from the source. Okay, and then in the next chapter we'll fix this for the propagation. We'll show how the propagation, finite speed of propagation, alters this. It's really pretty simple. It's not difficult. So this makes it clear then. Rho causes phi. J causes A. And then we have the gradient in phi can cause a force on a charged test body, or the changing A or the curling A can cause a force also on bodies. Okay, so that's why I really like to have the introduction of phi and A here, because it restores a sense of causality. You don't really have to go through E and B. You can do really work electromagnetism just doing phi and A. And in fact, when you get to, if you get to this course, it'd be a graduate level course, but if you get to this course, quantum electrodynamics, quantum version of E and M, called QED, quantum electrodynamics, you will work only in terms of phi and A. There's no explicit E and B. E and B are too difficult to work in quantum electrodynamics. And in fact, everything is done in terms of phi and A. And also in terms of the relativistic electrodynamics, where we show actually that Maxwell's equations are actually relativistic. It wasn't appreciated at the time, but they are. They do have a proper form for special relativity already in them. You just have to understand things in the right way to see that they are. Actually, even this you can get away with using phi and A. You can use E and B in that, but it's actually simpler to use phi and A again in the relativistic electrodynamics. Okay, so again, our understanding of phi and A. So let's go back and review here. Phi is the potential energy per unit charge, and A is potential momentum per unit charge. It's a simple physical understanding of those things. And a potential momentum per unit charge. Okay. Let's go back a step. In fact, one more step. Remember, we said so. We have potential energy now, and I want to trace back the origin of the potential energy here when we were talking about potential energy. Remember, we said that energy was frequently throughout physics we're using analogies. This is an analogy to another form of energy which we have a better understanding of. What was the analogate, the prime analogate that we point back to? Kinetic energy. So we understand potential energy in terms of kinetic energy by analogy, by some relation to kinetic energy. And so kinetic energy is our prime analogate. Okay. And so we're saying here that the phi field has an expression of a kind of potential energy. It's kind of related to a potential energy. Well, it certainly can be expressed physically by putting a charged body in there and then we see that it's the potential energy of that charged body per unit charge. But that phi exists even if we don't put the test charge there. So there's something present in the field which we could still call a kind of potential energy that's present in the field in a way. It's analogous to the potential energy of a massive body. So let's go back and remind ourselves the potential energy of a massive body comes from the understanding of kinetic energy. So let's go back to the kinetic energy again. Do you remember the argument for kinetic energy that I made, seems like ages ago, doesn't it? Okay, so I'm moving sand. I have a big pile of sand over here, and I want to move the sand, and I have different means of moving it. I have a little wheelbarrow, and I have a little, here's a little tricycle here like this with a little basket on the back of it. And then I have an RC car that can go 60 miles an hour here. Some of them do that. Little RC car. All right. And so they go different speeds. And I want to know which one is the most efficient means of transporting sand. So I'm going to put sand in here. And this one carries the most sand. This one carries a little bit of sand. This one carries maybe the least amount of sand, but it goes the fastest. So how do we figure out which one is transporting the sand most efficiently? Well, the transport of sand is a combination of two things, load and speed. So we have, in all cases, a load, how much sand, and a speed. And we could figure out which one of these methods, or any other methods, would transport sand the fastest. We want to both, the most load and the most speed, okay, or the combination of the two that would give us the most. Okay, but now consider a body here like a hockey puck that's sliding on the ice, and it has impetus, so it has a momentum that causes it to move. The impetus causes it to move in that direction. We have a momentum. Well, how fast is the momentum itself being transported? Well, the velocity, let's get rid of the vector here. The velocity is in the direction of the momentum, and it's proportional to the momentum by Buridan's law. So now we have the load is the momentum itself, and the speed by Buridan's law is proportional to the momentum. So that's the unusual thing here, right? I mean, in the comparison to transporting the sand, the speed of the vehicle doesn't really depend much on the load. Maybe a little bit, but not much. You know, you might see that it maybe slows down if it's got a heavier load, but not much. Right? The RC car, whatever, the tricycle, the wheelbarrow, the speed is pretty much determined by other things other than the load. But in this case, in the case of this body here, the massive body, how fast it's moving is actually dependent exactly on the load, on the momentum. And that gives us this factor of 1/2 up front, because the load is proportional. The load is proportional then to the speed is proportional to the load, and that gives us this factor of 1/2, which he works through, and I refer you back to that again. You might want to reread that. Okay, so the kinetic energy here is the rate at which the momentum or the impetus, the intensity of the impetus is transported. So it's another measure of the kinetic activity of a body. Okay, so now there's something like that in this field, phi. There's something like that. It's a potential energy. It's related, but there's no massive body here. It's not transporting momentum. Well, sort of. Not exactly. There's the potential momentum here that we have. And there is, in fact, in the book, an argument of the relationship between these two, that there is, in fact, a relationship between the potential momentum and the potential energy, as there should be, because there's a relationship between the potential energy and the momentum of a real massive body. There's a relationship between them because you have a force acting on it to make it move, to give it impetus, and then it moves as a result. Okay, so all of this is to say that there's actually lots of good reason to talk about phi and A as having physical significance. But we're going to understand phi and A as not being actual momentum or actual potential energy. Actual momentum or actual energy, excuse me, I can't say actual potential. Actual momentum or actual energy. So we're going to find in the next chapter that this radiating field, we have these sources that are generating electric and magnetic fields, and they propagate outward, and then through the parts of the plana, and then over here they can cause something to move. They can actually transport energy and momentum from the source out to the target and give that target now energy and momentum. So there's something like momentum and energy being transported through the plana. And that's the role of the phi and the A. It's kind of, in that sense, there's something analogous to energy and momentum that's being transported, but it's not energy and momentum in the primary sense, which is of a massive body. We talk about moving a massive body, the kinetic energy of a massive body and its momentum. So the plana carries momentum and energy, but analogously. We talk about it transports it. It doesn't have potential, it doesn't have energy and momentum like a massive body does, but it's by analogy. We can see that it carries something like that. Okay, and so that's where we're going with this in this chapter and the next chapter, is to give you a further understanding of the physical significance of phi and A. And in fact, so you're going to see the full Maxwell's equations. Well, in fact, I just wrote them down there earlier. You know, these are the full Maxwell's equations here. We've got the whole thing here when I wrote it up here. There they are. That's it. That's the full Maxwell's equation. So we've built our way up to that. But you can see in doing that, there's some possibility for confusion about what causes what. But if you just rely on phi and A, life is simple. It's not complicated. Okay, any questions? Okay, so I think your assignment for Wednesday is mostly reading chapter 5, right, on the last quasi-static effect. Maybe there's a couple of questions in there. So there's no plan to have a test until we get done with Chapter 6. So, 4, 5, and 6 will have one test. We're really not spending much time on Chapter 5. Chapter 5 is got a lot in it. We're skimming through parts of it, focusing on certain parts, focusing more on Chapter 6. Then there will be a test on Chapter 6. And let's see, also I should bring this back up. We were talking about we were talking about pizza for realists and also the recitation. So I'm going to hold this recitation on differently than what I told you. I'm going to hold the recitation on the 31st. So that's not this Thursday, but next Thursday. We'll have a recitation. And then we'll have, on the 21st of April, we'll go out. I think pizza. We got to find a suitable place. We'll go out to eat on the 21st. Rather than, I think I said the possibility was the 7th, I think. So I've made this more concrete now, altered it. We'll go out together on the 21st, but there will be a recitation on the 31st, a week from this Thursday, to work problems and things. Okay? All right. See you Wednesday.